Assalamu alaikum. This is lecture 15 of data security and encryption, and in this lecture we are going to continue our discussion about block cipher operations. In this lecture we are going to extend the advanced encryption standard modes for the block oriented storage devices, and we are going to discuss the tweakable block cipher storage encryption requirements, operations on single block and operations on a sector. Then there will be another kind of algorithm called format preserving encryption, in short for FPE. A motivation will be highlighted for using FPE, and there will be some difficulties in designing the FPE. And after that, I will discuss Feistel structure for format preserving encryption, and finally some NIST methods for format preserving encryption. So XTS-AES mode for block-oriented storage devices was approved as an additional block cipher mode of operation by NIST in 2010. The mode is also an IEEE standard 1619 2007. This standard describes a method of encryption for data storage in a sector-based devices such as hard disk devices or other mediums for storing data in database. So where the threat model includes possible access to stored data by adversary. And this kind of method has received a widespread industry support, and most of the current implementation of storage devices implement this standard. So XTS-AES mode is based on the concept of tweakable block cipher. Before examining the XTS-AES, let us consider the general structure of a tweakable block cipher. So a tweakable block cipher is one which has three inputs: a plain text P, a symmetric key K, and a tweak similar to the uh, plain text, or it can be different from plain text T. So a plain text P and a symmetric key K and a tweak T, and it produces a cipher output C. So you can write the statement much like the previous term, that cipher is an encrypted form of your key, your tweak, and your original plain text. However, the tweak need not to be kept secret, and it can be public. So the purpose of tweak is to provide the variability in the uh, cipher text, and the key is used to enhance the security. That is, the use of different tweaks with the same plain text and same key produces a different outputs. So if you change the T for the same plain text, your output will be different for each of the plain text. So the basic structure of several tweakable clock ciphers that have been implemented is shown in the figure. The encryption can be expressed in the combination of a tweak and a input plain text, and with two exclusive OR operators. So if you write the similar statement for tweakable cipher block, your cipher is equal to a combination of a hash function of your tweak, represented as T of j, and then you perform the hash function on T, which is XOR with uh, encryption of K and P, which we can write encryption of K along with the summation of XOR of H of T plus or XOR P. As you can see, the encryption of K, H, T or P is represented here, and the output of this function is again XOR with the hash function to produce the cipher. So as discussed, H is a hash function. Similarly, for decryption, the same structure is used with the plain text as input and decryption as the function instead of a encryption. So only change here is the function of the encryption is replaced with the function of decryption. Rest is the same. You combine the hash function with the input, perform the exclusive OR, then perform the decryption, and then on the output perform the hash function exclusive OR with the decrypted value to actually get the final outcome of the plain text. So it is easy to construct a block cipher mode of operation by using a different tweak value on each block. In essence, the ECB mode is uh, used for each block of the tweet, and it is changed for each block. This overcomes the principal security weakness, which is that two encryption of the same block yield the same cipher text. So the next topic is storage encryption requirement. So the requirement for encrypting stored data, also referred as data at rest, differ somewhat from those for the transmitted data. So in these cases, we are discussing about the storage devices in which there is no communication or no transmission of data over the channel, but the data is stored in a in a storage medium. So the standard P1619 was designed to have the following characteristics, and among these characteristics that lead to this situation are the ciphertext. The first one is the ciphertext is freely available for the attacker. That for your storage devices, the ciphertext is somewhat available for your tracker. So a group of users that have authorized access to database, some of the record in the database are encrypted so that only specific user can successfully read or write them. So other users can only retrieve the encrypted record but are unable to read it without the key. Similarly, the next characteristic states that the data layout is not changed on the storage medium and in transit. The encrypted data must be the same size as the plain text. So the layout is not changed for the stored data in plain text or in ciphertext form. The data are also accessed in fixed size blocks independently from each other. That is, an authorized user may access one or more blocks in any order. On storage medium, this encryption is performed in 16-byte blocks independently from each other, except when the data is less than whole block, the encryption may differ from the rest of the blocks. So there are no other metadata used except the location of the data blocks within the whole dataset, and the same plain text is encrypted to different ciphertexts at different locations, but always to the same ciphertext when written to the same location again. And a standard conformant device can be constructed for decryption of data encrypted by another standard conformant device. So the P1619 considers some of the existing mode of operation for use with the stored data. So the counter mode, an adversary with the right access to the encrypted media can flip any bit of the plaintext simply by flipping the corresponding ciphertext bit. So consider the requirement 6 in this case to use of CBC to enforce the requirement that same plaintext encrypt to different ciphertexts in different locations. The initialization vector could be derived from the sector number. So each sector contains multiple blocks, and adversary with read-write access to the encrypted disk can copy a ciphertext sector from one position to another, and application reading the sector of the new location will still get the same plaintext sector. For example, this means that the attacker is allowed to read the sector from the second position but not from the first. Can find the content of sector in the first position by manipulating the ciphertext. So another weakness is that attacker can flip any bit of the plaintext by flipping the corresponding ciphertext bit in the previous block, with the side effect of randomizing the previous block. So this figure shows an encryption and decryption of single block. The operation involves two instances of AES algorithm with two keys, key 1 and key 2. There are certain parameters that are associated with this uh, single block operation of XTS-AES. So first of all, there is a key, the 256 or 512-bit AES key can be used. And there are two keys, so this is passed as a concatenation of two fields of equal size called key 1 and key 2, such that key 1 is equivalent to key 2. The next component of this algorithm is the plaintext, and it is referred as P of j, and this is uh, the jth block of the plaintext, and all blocks except possibly the final block have length of 128 bits. That every block is a fixed length, and plaintext data unit typically is a disk sector consists of a sequence of plaintext blocks ranging from P1 to Pm. And then there is a cipher referred as C of j, and it is the jth block of the ciphertext. All blocks except the possibly the final block have the length of 128 bits, similar to the plain text bits. The number I and j are the sequential number of the 128 bit block inside the data unit, and j is used for the plain text and the ciphertext, and I is the value of the 128-bit tweak, and it can be tweak values are assigned consecutively and starting from an arbitrary non-negative number. Then there are some other elements referred as alpha, which is a primitive element of Gaussian field 2 raised to the power 128 bit that correspond to a polynomial function. And there are bitwise exclusive OR operator, which is similar to the simple exclusive OR operator discussed earlier, and there is a modular multiplication of two polynomials with binary coefficient of modulo x raised to power 128. So if you look at the diagram, the internal bits of the tweak are embedded with a key using an AES encryption algorithm, which is multiplied by alpha, and which is again uh, exclusive OR with the input plain text, and another key is applied along with an exclusive OR to produce the cipher text. On the other hand, decryption involves the same process except from the input is changed from plain text to cipher text. So the plain text of a cipher of a sector or a data unit is organized into 128 bits or for each block. Blocks are labeled by P0, P1 up to P of M. The lost block may be null or may be contain any number of bits from 1 to 127. In other words, the input of AES algorithm consists of M 128 bits blocks and possibly final partial block. For the encryption and decryption, each block is treated independently and encrypted or decrypted values can be excluded can be found out after the XTS-AES block encryption and XTS-AE block decryption. The only exception occurs when the lost block is less than 128 bits. In that case, the last two blocks are encrypted decrypted using cipher text stealing technique instead of padding. So as this figure shows the scheme, the PFM-1 is the last full plain text block and PFM is the final plain text block and CFM is the final ciphertext block. Similarly, CFM-1 is the second last or block of ciphertext. So the technique is commonly called ciphertext stealing because the processing of lost blocks steals a temporary ciphertext from the second last block of the complete cipher block. As you can see here that if CFM is the final block and there is no further value, CMM can be considered as final block. So as it can be seen through the AES mode like counter mode, it is suitable for parallel operations because there is no chaining and multiple blocks can be encrypted or decrypted at the same time. So unlike counter mode, this mode includes a parameter I as well as a counter j. However, in the counter mode there was only one parameter named as nonce. So the another important encryption algorithm is format preserving encryption. So it refers to any encryption technique that takes a plain text in given format and produces the ciphertext in the same format. For example, the credit card consists of 16 decimal digits. So if we apply a format preserving encryption that can accept this type of input would produce a ciphertext output of 16 decimal digits. Note that the ciphertext need not to be in fact and unlikely to be a valid credit card number. That means this number can be an invalid number in the ciphertext, but it will have the same format and can be stored in the same way as the credit card number plain text. So a simple encryption algorithm is not format preserving, with the exception that it preserves the format of binary strings. Other than any uh, formatted data, the encryption algorithm will change its format. For example, this table shows that three types of plain text for which it might be desired to perform a format preserving encryption. The third row shows example of in hexadecimal and in simpler form of what might be generated as an format preserving algorithm. So as you can see, the credit card numbers are described in an AES hexadecimal format. Format preserving encryption algorithm is very useful in many applications, especially it is retrofitting of encryption technology for the legacy application. The legacy applications which do not want to change their data types or where the conventional encryption mode might not be feasible because it would disrupt the data fields. So FE is very useful for legacy applications. FE has emerged as a useful cryptographic tool and its application include financial information security, data sanitization, and transparent encryption of fields in legacy databases. The principal benefit of FE is that it enables protection of particular data elements while still enabling workflows that were in place before the FE was in use. So it means that if you apply FE on the database, no database schema changes and minimum application changes are required. So only applications that need to see the plain text of data element need to be modified, and generally these modifications will be very small. So some examples of legacy application where FE is desirable are COBOL data processing application, and in such application any changes in the structure of records requiring corresponding changes in all the code references that record structure. So typical code sizes involve hundreds of modules, each containing about 5,000 to 10,000 lines on average. The other applications can be database applications in which the fields that are specified to take only character strings cannot be used to store conventionally encrypted binary ciphertext. So the encoding of such binary ciphertext is not always feasible without the increase in data length. So it requires an augmentation of corresponding field lengths. So FP encrypted characters can be significantly compressed to their efficient transmission. However, there are many difficulties in designing an FPE even for the legacy application. A general purpose standardized FPE should meet a number of requirements. First of all, the ciphertext is the same length as the format of the plain text. So it is a very difficult requirement to meet for many applications that ciphertext must be of the same length and the format as the plain text of application must be same for ciphertext and the plain text. Another difficulty it must meet that it should be adaptable to work with a variety of characters and number types. These examples include working with decimal digits, lowercase alphabetic characters, and the full character set of standard keyboard and international keyboard. And it should also work with the variable plain text length. And security trends should be comparable to that achieved with the AES, that you must have a high level of security in the FPE as well. And security should be strong enough even for the small plain text lengths. So meeting the first requirement is very much difficult. A straightforward encryption with the AES yields a 128-bit binary block that does not resemble the required format. That AES changes the plain text to another format, and also a standard symmetric block cipher is not easily adaptable to produce an format preserving encryption. So as we discussed in the last slide, the challenge with the FPE is to design an algorithm for scrambling the plain text that is secure, it preserves the format, and it must be reversible. So a number of approaches have been discussed in the recent years for FPE algorithms. The majority of these proposals use the Feistel structure discussed in the lecture number 8 or 9. The Feistel structure can be used to implement an FPE algorithm. So this figure shows a Feistel structure used in all of the NIST algorithms, with encryption shown on the left side and the decryption shown on the right side. However, for the simplicity of the presentation, the illustration of swabs that was used in the Feistel structure is omitted in this diagram. So as you can see, the process of decryption is essentially the same as the encryption process. The differences are the addition function is replaced by a subtraction function from encryption to decryption, and the order of round indices are reversed, which was very much similar in many of the applications that you start from round 0 to round n in the encryption, and then you reverse the round in the decryption. To demonstrate that the decryption produces the correct result, it shows that the encryption process going down the left hand side and the decryption process going right to the up hand side. The diagram indicates that every round the immediate value of the decryption process is equal to the corresponding value of the encryption process, which we have verified when we discussed the implementation of Feistel structure. There are some algorithm which requires character string. So the NIST and other FP algorithms have been proposed that also use the plain text consisting of string of elements called characters, and a finite set of two or more symbols of characters are called alphabets, and the elements of the alphabets are again called characters. A character string is a finite sequence of characters from an alphabet. It means it can be a word of alphabets. Individual characters may repeat in the string, which is similar to our English or other alphabetic alphabets. The number of differences and the number of different characters in an alphabet is called the base, also referred as the radix of the alphabet. So the number of different characters in English are 26. So the radix of English is 26. If we refer to the radix of a binary number, it is 2. If we refer to the radix of integers, it is 10 decimal numbers. So the NIST document defines the notation for specifying these conversions. To begin with, it is assumed that the character string is represented by a numerical string, and to convert a numerical string x into a number x, the function number is defined. Viewing x as a string, which is a part of substrings x1 to xm. So these are different definitions. The first notation states that x converts an integer into a byte string. It is the string of s bytes, and it is represented as x power s that encodes the number of x with x is greater than 0 and it must be less than 2 raised to power 8s, where s can be any number of bits. It is equivalent to the notation string 2 of s is equal to s. The length of x specifies the length of character in the string, and the number of radical x we have already defined. It converts the string to the numbers. The pseudo-random function prfk of x that produces a 128-bit output with x as input and using the encryption key is referred as prfk of x. Again, string m of radix given a non-negative integer x less than the radix m. The function produces a representation of x as a string and m characters in the base radix. It is the most significant character first. I to j is the set of integers between two integers I and j including I and j. Similarly, I to j is the substring of characters with an x from xi to xj, including xi and xj. Reverse of x is given a bit string. X is the string consists of bits x in reverse order. So this table shows some parameters used in format preserving encryption, and the one parameter we discussed is the radix, which is the base of the number of the characters in given plain text or alphabet. Then there can be a tweak. It is an input parameter to the encryption and decryption function whose confidentiality is not protected by the mode. It can be public. Then there is a tweak radix for the base for the tweak strings. Then minimum length, maximum length specify the minimum message length and maximum message length respectively, and max t length specifies the maximum tweak length. So after covering these basics notations and parameters that will be used in FPE algorithms, let's move our discussion to the NIST methods for format preserving encryption. In 2013, NIST issued SP800 recommendation for block cipher modes of operations and methods for format preserving encryption. This recommendation specifies three methods for format preserving encryption. These methods are called FF1, FF2, and FF3. They employ the somewhat different round of functions which are built using the advanced encryption standard, and important differences can be listed as below. So the FF1 supports the greatest range of length for the plain text, character string, and the tweak. To achieve this, the round function uses the cipher block chaining (CBC) style of encryption, whereas FF2 and FF3 employ simple electronic codebook encryption. On the other hand, FF2 uses a subkey generated from the encryption key and the tweak, whereas FF1 and FF3 use the encryption key directly. The use of subkey may help to protect the original key from the side channel analysis, which is an attack based on information gained from the physical implementation of crypto system rather than the brute force or cryptanalysis. Examples of such attacks are attempts to reduce the key bits based on power consumption of execution time. And FF3 offers the lowest round of count 8 compared to the 10 in FF1 and FF2, and it is least flexible in the tweaks that it supports. So the algorithm FF1 was submitted to NIST as proposed FPE mode with the name of FFX radix. FF1 uses the pseudo-random function prf of x that produces a 128-bit output with the input x. So it takes the input x and produces a 128-bit output, and it also produces an encryption key. In essence, PRFK of x uses the CBC encryption with x as the plain text input, encryption key k, and initial vector IV of all zeros. The output of the lost block is the cipher text produced. So it takes the 128 block cipher and a cipher function key for the block cipher. Inputs are string x, and it takes the length of x, and it provides an output of 128-bit block y. So as referred earlier, the algorithm FF1 is referred as FFX of radix, and the FF1 encryption algorithm is illustrated Here, the shaded lines correspond to the function fk. The algorithm has 10 rounds and number of parameters. So the first parameter is the radix. That means it can operate on 16 bytes. So its radix can be from 2 to 2 raised to power 16. And there can be minimum length of radix, and the algorithm states that the radix minimum length must be greater than 100, and minimum length of the string must be greater than or equal to 2. Maximum length must be less than 2 raised to power 32, and maximum tweak length must be equal to or less than 2 raised to power 32 values. So the input to the encryption algorithm are character string x of length n and a tweak t of string byte length t, such that t is belong from max length of t, which is 2 raised to power 32. However, the tweak is optional and it may be an empty string. So if you look at the output, output can be a character string with a length of y to n. So first two steps of the algorithm take the input x and split into two substrings a and b. So if n is even, a and b are equal length, otherwise b is one character longer than a, as represented in first two lines. The third step illustrates that the expression v log 2 of radix equals to the number of bits needed to encode b. It actually requires the number of bits to encode the second part of the string, which is v characters long, as depicted here. V is equal to n minus u, and u was n divided by 2. So the definition of D ensures that the output of the Feistel round function is at least 4 bytes longer than this encoding of B, which minimizes any bias of modular reduction in the step 5. So step 4 describes about the plain text, which is 128-bit or 16-byte block, and that is function of radix, the two values left hand and the right half, u and n, and a tweak t. So it serves as the first block of the plain text input to CBC encryption mode used in the next step. So the next step, step number 5, is a loop from 0 to 9. That means it takes 10 rounds of encryption, and the function is highlighted in the shaded box. And the first step states that the tweak t of the substring b and the round number along with I are encoded in a binary string q, which is one or more 128 bit blocks in length. So you can first note that the value of number of radix b produces a numerical string that represents the b in the base radix. The step 2 of shaded area concatenates p and q and input to the pseudo random function p or f to produce a 128-bit output or. This function is a pseudo-random core of the Feistel random function, which was already discussed earlier, and it scrambles the bits of our input b of I. So the third step in the shaded area either cuts or expands the R to a byte string S of length D bytes. So if D is less than 16 bytes, then R is the first D bytes of R. Otherwise, the 16-byte R is concatenated with the successive encryption of R, and XOR with the successive constants to produce the shortest string of 16 bytes block, whose length is greater than or equal to D bytes. So the fourth step begins with the process of converting the result of the scrambling of B into form of suitable combining with the A. So in this step, the D byte string S is converted into a numerical string in the base 2 that represents S. So that is, the S is represented as a binary string value Y. The fifth step of the shaded area determines the length of M of the character string output that is required to match the length of B portion of the round output. For even numbered rounds, the length is U character, and for odd number rounds, the length is V character. And the sixth step calculates the numeric values of A and Y are added to the modulo radix. This truncates the value of sum of value of C that can be stored in M characters. Finally, the step converts the C into the proper representation of as a string of M, and these steps complete the round by placing the unchanged value of B from the preceding round into A and placing C into B. So after the final round, the result is returned to the concatenation of A and B. Similarly, the algorithm FF2 was submitted to NIST as a proposed FPE mode with the name of VAES3. The encryption algorithm is defined in the figure represented here. The shaded line corresponds to the function f of k. The algorithm has the similar parameters except the radix is less here, which is from 2 to 2 raised to power 8, and we have same length of tweak, which is less than 2 raised to power 8. Again, radix length can be greater than 100, and minimum length of at least 2 bits, and the maximum length must be formula that must be less than equal to 2 or 120 log 2 radix. For FF2, the plaintext character alphabets and that of the tweak may be different. So the first two steps of FF2 are the same as FF1, setting the values for U and V, and then setting the values of A and B. So the third step again is the input of plain text P into 128-bit block. If there is a tweak, then P is a function of radix and the tweak and the N, and then 13-byte numerical value of the tweak. So if there is no tweak, in other words P is empty, well, then the P is a function of radix of N and P is used to form the encryption key in the step 4. So in the step 4, J is the encryption of P using the input K. And step 5 again is a loop from 0 to 9. That means it will again repeat for 10 times. So in FF2, the first block of shaded area converts B into a 15-byte number and prepend the round to the block from the 16-byte block Q, and Q is encrypted using the encryption key J and yield Y. So the remaining of steps are same as FF1. The essential difference is in the way in which all the parameters are incorporated into the encryption that takes place in the block FFK. In both cases, the encryption is not simply an encryption of B using key K. For FF1, B is combined with the tweak, the round number T and U and radix to form a string multiple of 16-byte block. Then CBC encryption is used with the K to produce a 16-byte output. So for FF2, all of the parameters beside B are combined with to form a 16-byte block, which is then encrypted with a K to form the value of key J, and J is then used as a key for the one block of encryption of B. The algorithm FF3 was submitted to NIST as proposed FPE mode with the name of BPS-BC. The encryption algorithm is illustrated here. The shaded line again corresponds to the function f. The algorithm has similar parameters to the function, the algorithm ff1. So in this case, the tweak length is sure, and it has to be about 64 bits. So FF3 proceed with the number of steps which are very different from other two. The first two steps, the input is split into the two string A and B, which are similar to the FF1 and FF2. If n is even, A and B are both equal length, otherwise A is one character longer than B, in contrast to FF1 and FF2 where B is one character longer than A. So in this case A is larger than B. So in the third step, the tweak is partitioned into 32-bit left tweak TL and 32-bit right tweak TR. In the fourth step, the loop through the 8 rounds for the encryption. So the shaded area states that as in FF1 and FF2, this step determines the length of M of the character string output that is required to match the length of B portion of the round output. The step also determines whether the left tweak or right tweak will be used in word in step 2. So the bits are reversed in step 2, then number radix produce a 12-byte numerical string in base radix. The results are again reversed and a 32-bit encoding of round number I is used in a 4-byte unit, which is reversed and then XOR with the W and P. In the third step, P is encrypted using the encryption key K that yields Y. And the fourth step is similar to the step in FF1 except that Y is reversed before converting it to a numerical string in base 2. So the step 5 is outside the function K, and it is the numerical values of reverse of A and Y are added to the modulo radix M. This truncates the value of sum of values C that can be stored in M characters. So the final step converts the C to a numerical string C. The remaining steps are same as FF1. So this concludes today's lecture, and in this lecture we discussed about the tweakable block ciphers, and we discussed some encryption requirements for storage on storage mediums, and finally we discussed some format preserving encryption algorithms. We identified the motivation and difficulties in designing a format preserving encryption algorithm, and then we studied how a Feistel structure can be used in a format preserving encryption algorithm, and finally we overviewed three methods of NIST for format preserving encryption algorithms. So you can read the chapter 7 for further information about the topics, or you can ask me a question and answer session. Thank you very much.